Hi everyone, how are you people doing? So first of all, let me welcome you guys to the Unacademy JEE English, and this is a brand new channel by Unacademy, which is India's largest online learning platform for IIT JEE. And on this channel, everything is being taught to you completely in English. So this is a series that I host for class 12 students, and the topic that we are covering right now is current electricity. This is lecture number 7, and today we'll be talking about electrical power. Hi Osho, hi Rohit, how are you guys? Okay. So let's get started. Before I get started, let me introduce myself for those of you who might not know me. So my name is Rohit Dixit. I studied mechanical engineering from IIT Delhi, and for almost past 8 years now, I've been teaching physics for the JEE exam. I myself was All India rank 447 and All India rank 192 in the two stages of JEE that I gave, and I had qualified the NTC stage 2, and I was also in the top 1% in the NSCP. I've also coached many students to top ranks in the IIT JEE in the offline setup. Now I hope to continue mentoring you guys to top ranks with the Unacademy. So yes, Osho, yes, I have been a little busy with some work. Okay, so yes, that is why I was not taking sessions for the past 2 3 days. Hi Chinmay, how are you? Okay, Shivendra Pratap. So ले लिया भाई आपका नाम. I hope you're happy now. So as I was saying that in this lockdown, when I as a teacher was also forced to move to online options, online teaching. Before this I told you all my teaching had been offline. So similarly, I know you guys also must be feeling the problems of the lockdown. You can't attend your offline classes, and you can't even afford to let your studies get affected because of that. So what do? You can get your Unacademy subscription and make sure that your studies go uninterrupted. Now, your Unacademy subscriptions will give you benefits like live classes. You get to interact with your educators on a regular basis. You have live polls and leaderboards. You have test series and analysis, and you have live doubt clearing sessions. So this also ensures that your doubts are never piling up. You always get your doubts sorted, and you have interactive lessons where the learning is pretty effective. From now onwards, I'm going to watch every session live. Good, Shivendra. Do that. Now, as I was saying, on top of all these benefits, you are getting access to India's best educators with your Unacademy subscription. So, Unacademy is providing you the opportunity to study from the top educators across the entire nation from the comfort and safety of your home. So, how do you get this subscription? How do you make use of these benefits? Very easy. So, all you need to do is install the Unacademy app. Once you have done that, go to the plus section in your app, select your goal as IIT and click on Get Subscription. Now, when you are paying your subscription fees, you will be asked, do you have a code? That is where you can use this code, RD Life. This is my code. When you use this code, you will get a 10% off across all your subscription fees. So make sure you're getting your subscriptions as soon as possible, and make sure you're using this code and availing this discount. Okay, so for those of you who are following us on the JEE English channel, can connect with us on the Telegram app using the link shown above. Yes, Chinmay, I know. After a long time. So yes, I had been not taking sessions for the last 3 days. No, I was not ill. I was just busy with some work. Okay. See, I take sessions like 7 days a week, so I hardly get any time to take care of, a lot of stuff. So it had been piling up. That is why I decided to take 2 3 days off, take care of everything at my end, and then get back to my classes. Okay. So let's get started without any further delay with today's discussion. So today I told you we will be discussing about electric power. So first we will talk about the heating effect of current. So what is that? You have studied this already in class 10. You know that when current flows through a conductor, heat energy is generated in the conductor. Now this heating effect of the current depends on three factors: the resistance of the wire, the time for which the current is flowing, and also the amount of current flowing. Yes, Shivendra, on Unacademy Plus, my course is starting. Two courses are starting from 5th and 6th of October. Okay, so that is where you can find me on Plus. Okay, when is 11th session? So 11th session would be tomorrow, Chinmay. Okay. Now again, The heating, the heating effect produced by the flow of current I through a conductor of resistance R in a time t can be measured as H equals I square RT, and this equation is known as Joule's law of heating. So first of all, let's try and understand how are we getting this equation. So you know that the potential difference. So consider a resistor. Consider a resistor, and let's consider that the potential difference across both its ends is V. Okay, so let's say, so there is one end A and one end B, and the potential difference across this is V. And imagine the resistance here is R, and let's say if some current I is flowing through it. Now you realize the current I, when the current I is flowing, so small charges are continuously flowing. So let's consider the flow of a charge dq. Imagine a dq charge flowing from end A and reaching end B. Now you realize that why will the charge flow? Because there is a higher potential here, there is a lower potential here, and there will be an electric field in the conductor that would be pushing this charge from the higher potential to the lower potential, right? So you will have electric field inside the conductor like this from A to B, and this electric field is pushing the charge. Now when it reaches from A to B, this electric field would have done some work. However, we realize that in electrical circuits, all the charges move with continuous speeds, which we call drift velocities, right? Okay, so quality of my lectures would be very similar. The only difference would be that in plus there would be more extensive, practicing, and you will get DPPs. There will be problem discussion sessions, and that's about it. The quality of teaching, the content is almost going to be at least 95% the same. Okay, because I am covering every topic, everything about all the topics here only. The only difference with plus is one, you have a regular schedule, you have regular tests also there, you have test analysis sessions, you have quizzes, you have doubt clearing sessions, okay, and you will have practice sessions also, regular practice sessions. So those are the benefits. As far as the concepts is concerned, as far as the teaching of the ideas and fundamentals is concerned, it's going to be the same. There you will just get a little more rigorous practice and let's say a personalized guidance about how you should be improving and where you're going wrong. Okay, so as I was saying, so what will be the this electric field would do some work on this charge, and I know work done by electric field dw would be equal to the potential difference times dq. Okay, I hope you remember this from the definition of your potential difference. Okay, all right, Chinmay, sure. Right. So we discovered that that'll be the work done by electric field. By definition of potential difference, potential difference is the work done per unit charge in bringing any body from point A to B. Now you realize if work is happening, then my kinetic work energy theorem tells me that there should be a change in the kinetic energy of the charge. However, we realize that all these charges are only moving with a constant velocity v drift. So what does that mean? Bye, Chinmay. Take care, and I will see you tomorrow. So that means that there has to be another force which is doing work on it, and it must be doing negative work, which we know now is the work done by resistance. So I can say that let the work done. So resistance is the force that is opposing the flow of electrons, the free flow of electrons. So the kind of work it would be doing would be negative. So that makes sense logically also. So let the work done by the resistance equals dWr on this charge when it moves from it across this resistor. Now I know from work energy theorem, I know that net work done by all the forces should be equal to the change in kinetic energy of the charge. Okay, so I would get that WE plus dWr would be equal to 0. Okay, the work done by the electrical field plus work done by the resistance has to be 0 because we don't see any change in the kinetic energy of these charges. So from here I get the equation that dWr equals minus times V dQ. Now I can also replace a dq as I dt. So if dq was the charge that passed through this in dt time and I was the current, then I can say that dq would be nothing but I times dt, because I by definition was dq by dt. So if I substitute that, then what I get is that dw equals minus vi dt. Now all I need to do is integrate this. So I will get that the work done by resistance is minus VIT. Now I can substitute from Ohm's law, V equals IR. So this becomes minus I square RT. Now you realize the negative work that the resistance is doing. This is the amount of energy that it will be dissipating to the environment. Okay, this is the energy that it is extracting from the free flowing electrons. So this would be the heat that would get generated across the resistance. Okay, it's like friction. When friction takes kinetic energy by doing negative work, it dissipates it all in form of heat and sound. So similarly, when resistance is doing negative work on all the free electrons which are flowing in the conductor, this negative work is actually the amount of kinetic energy that it took away from those free electrons. This will be the same amount of energy that it will end up dissipating. Okay, so now you have the formula and now you know how you get I square RT. Next, we will talk about electrical power. Now, electrical energy converted into some useful work by an electrical device per unit time is known as power of the device. Now, we already know that the work done by the resistance is the negative work done by the resistance is the amount of energy available with that resistor which we can utilize in form of heat, in form of light, or any which way that we like. So it can also be defined as the amount of work done by an electrical device per unit time, and the work is being done by resistance only. Okay, so you will realize that the power transferred to a load by a cell. So load is the device across which we want to use this power, across which this power should be dissipated. So that would be I square times R, where R is the resistance of that load. Okay, so if you have a circuit like this, where you have a cell of EMF E and internal resistance R, and you join this with an external resistance, and this is what I'm calling my load. This is where I want my power to be dissipated. So this load resistance is representative of anything. It can be any electrical device. Okay, so the idea is that I want to use the power stored here, the chemical energy stored here in the cell in form of electrical energy. That electrical energy, when passing through here, can again be converted into other forms. So that is our idea of using electrical circuits. That is why we are analyzing this, because once we do that, now we can convert the chemical energy stored in cells into first the electrical energy, and then that electrical energy can be converted into other suitable forms of energy as per our requirement. Like you have electric bulbs where most of the electric energy is converted into light. Similarly, you would have heaters where most of the energy is converted into heat. You can also convert this energy into mechanical energy. We will see that how we do that in motors. So, but right now let's just focus on what kind of power is available for us. So whatever power gets dissipated across the resistance, whatever negative work the resistance is doing, that is the work that we can extract from it. Okay, that is the electrical power of any device. So why don't we start with a practice problem, a very, very simple problem. So here you've been asked in an electrical circuit having two resistors, 2 ohm and 4 ohm respectively, are connected in series with a 6-volt battery. As you can see, you have to find the heat dissipated by the 4 ohm resistor in 5 seconds. So this is the simplest possible question that I have got for you, just to get you warmed up, just to get you a bit of practice. So why don't you guys try this? And let's see if you can get this right. So please try this problem. This is a very, very simple problem. Should not be any problem at all. Let's quickly have some answers. Okay, are you guys trying? Okay, I can see a few people online, but I don't know what they're doing. So I would like you guys to try this if you can. Let's wait for 2 minutes. This is very, very simple. So I want you to solve this and give me a quick answer. Hurry up, hurry up. This is just for your practice. So try and give it a shot and give me an answer quickly. Okay. So again, guys, I keep encouraging you for more participation. So you guys, I can see yes. Okay. No AP. I don't think C is correct. Let's see. This was a very simple one. You have two resistors of R1 and R2 in series. So that makes the equivalent resistance as 6 ohms. You have that connected with a 6-volt battery. So you realize in this question the current across the circuit I would be 6 over 6 equals 1 ampere, right? So that will be the I. Now you know across any resistor, the heat generated is I square RT. So I means 1 into R. We are talking about the 4 ohm resistor, and you've been asked to calculate the heat across it in 5 seconds. So 20 joules would have been your answer. Okay. So option D is the right answer. But I'm glad you tried and good. Next, you've been asked that when a battery sends current through a resistance R1 for time t, the heat produced in the resistance is Q. If the same battery sends current through another resistance R2 for the time t again, the heat produced in R2 is again Q. So then determine the internal resistance of the battery. So try this question. This is slightly tricky. Let's see if you can give me the answer for this. So what happened to Osho Kothari? Where is he? Okay. So let's try this. Let's quickly try this. So I'll give you 2 minutes to try this. This because it's a slightly tricky one, not too difficult though. It just may confuse you a bit. That's about it. So try and solve this quickly and yes, AP, that is correct and that was very fast. Very well done, AP. So very impressive. Yes, that is correct. So this is very, very simple. So for the first case, for case 1, so let's just draw a circuit, okay? So you have a resistance R1 here, and then you have a battery having some internal resistance, so battery of EMF E and internal resistance R. Okay, all right. Well done, well done. So for case number 1, you know that the I through this, I would be EMF over R plus R1. Now, what have you been told that in time t, The heat dissipated across R1 is Q. So, and Q equals I square R1 times T. Right. Similarly, I can say, similarly, in case of second uh, circuit, I dash in second circuit, that would be again EMF plus R2 now. See, the EMF and the internal resistance of this battery would be the same. Only thing that would have changed was instead of R1, I am putting R2 there. Okay. So now you also know that Q would also be equal to I dash square R2T. So all I need to do is equate 1 and 2. So from 1 and 2, what you will find out is that E square over R1 plus small r whole square R1 would be equal to E square over R2 plus R whole square into R2. So obviously this goes, this goes. What you are getting again is, if I take the roots, then you are getting root R1 over R1 plus R equals root of R2 over R2 plus R. So now all I need to do is just cross multiply this, and let's see what we are getting then. So if I cross multiply this, I am getting R times root R1 minus root R2, and that would be equal to R1 R2 minus R2 R1. So all I need to do is take root R1 R2 common, and let's see, if I take root R1 R2 common from here, I can say that small r into root R1 minus root R2. Now this would be equal to root of R1 R2 times root R1 minus root R2. So yes, this gets cancelled and you get small r equals root of R1 R2. Okay, I hope everybody followed that. I will give you 1 minute to go through the solution and let me know if you have any problem with any of these steps. Okay. So it's very simple. We just wrote the equations for both these circuits and then we just equated them. Okay. So trust me, there's nothing too difficult about this. This is a simple problem. Okay, hope you have gone through this entire solution, and if you have any issue regarding any of these steps, you can write so in the chat, and otherwise I will move forward to the next part of the discussion. Let's see. Okay, so seems fine with everyone, I guess. Okay, let's move ahead. Next, I wanted to discuss something called maximum power transference theorem. So imagine that you have a circuit in which you have a battery and then you have an external resistance. So if I wanted to decide what value of capital R should I take so that this battery can dissipate the maximum amount of power. So let's try and see that. So I already know that for the circuit shown above, for the circuit shown above, the value of I is epsilon over R plus R. So what is the power which is getting transferred across capital R? Therefore, power transferred or power dissipated also you can say across R1. How will that be? That will be I square times R1, and which I can say is epsilon square over r plus r whole square into r. So this is the expression that you are getting for power. Now, if you want to draw a graph of this, you will realize the graph would come like this. If this r is 0, then you will get 0. And as you increase the r, this power will increase slightly, it will reach a maximum and then it will start decreasing. Okay, so our aim is to find the value of r for which the power dissipated would be maximum. So you should know how to do that. If this is a power and r is the variable that I can change, so I can change capital R. Okay, so capital R is what I can change, and I'm trying to see its relation with power. Now, what do I need to do is I will differentiate this. So let's do that. So what happens if I find dp over dr? So dp over dr, what I usually like doing is that I like using product rule here also for differentiation. So the first term would be this plus the second term would be this into derivative of this. So this would be r plus r to the power of minus 2. Derivative would be minus 2 into r plus r to the power of minus 3, and this entire thing should be 0 for maxima. Okay, so from here what I am getting is that e square over r plus r whole square should be equal to 2 times e square capital R over r plus r whole cube. So this and this gets cancelled, this and this gets cancelled. What I get here is that small r equals capital R. So that is the result, and that is what we call maximum power transference theorem. That in order to transfer maximum amount of power from a battery, the external load resistance should be equal to the internal resistance of the battery. Okay, so let's just write it down in a statement. So thus, a battery delivers maximum power across an external load or external resistance. So it's one and the same thing. We generally call it load only. Load when the external resistance capital R equals small r, which is the internal resistance of the battery. So please remember this. This is known as maximum power transfer theorem. This is known as. So this is a standard result. You can directly use this result anywhere in your problem solving now. Maximum power transfer theorem. And you will realize that this maximum power would be equal to E square over 4R. Why? The current would be E square over 2R, and the value of capital R will be equal to small r. So when you calculate the value, it will come out to be E square over 4R. And this is the kind of graph that you will find between power and the resistance R. You will also realize that at this value, the current from flowing across the R is also maximum, and the potential difference across the capital R is also maximum. I hope you can see that, everything like that. Why? Because you realize if I is changing, R is constant, so power was I square R. So you realize when this is maximum, since this is constant, this has to be maximum. So I can say that at R equals R, not only your power is maximum, I is also maximum. If I is maximum across this, then I can say that the potential difference across R is also maximum. Therefore, V across load is also maximum. So, you can be asked for this different situations. One, you can be asked find the condition for which the power across the capital R is called maximum. In that case, of course, the condition becomes that internal resistance of the battery should be equal to the external load resistance. Or you could have been asked find the condition where the current across R is maximum. Or you could have been asked find the condition for which the potential difference across the load is maximum. For all these conditions, they essentially mean the same thing, and the condition would be that small r should be equal to the r external. Okay, so I hope everybody followed that. If you have any doubt regarding anything discussed on this slide, please let me know. Otherwise, I will move ahead. I think this is a simple enough derivation, only simple enough proof. So it should not be too difficult to follow. But is in any case, if there is some step that you missed, if there is some step that you don't understand, then let me know and I will go over that one more time. Okay, just take a look at what we did. So we took a battery of EMF epsilon and internal resistance R. Now I wanted to decide for what value of capital R joined across it will result in the battery delivering maximum amount of power. So we realized that the condition for that was that the external resistance should be equal to the internal resistance, and this will be the kind of graph if you plot it. Of course, as r tends to infinity, if r tends to infinity, you will also realize that again the power would again start tending to zero. Why? Because the current would start tending to zero. Okay. Okay. So I guess everybody's fine with this, right? So let's have a practice problem. Now here it says a total of 24 identical cells. Okay, so that should be identical. 24 total of 24 identical cells of EMF 2 volt and internal resistance of 0.5 ohm each are to be connected so that there are m rows of n cells connected in series in each row. So there have to be m rows, and in every row there has to be n cells which are connected in series. You have to find the value of m and n for which the power dissipated across an external load of 5 ohm is maximum. So try this and let's see. Let's see you guys try this and solve this very, very quick. Okay, Aditya, I don't remember you. It's been a while. I think I do remember the name somehow. And I told you V directly proportional to root T. Yes, 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 yes. Yes, now I remember. All the V's were directly proportional to root T. Yes, 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 yes. Your whether be it VRMS, it is something something into T, or your V most probable, that is also something something here into capital T. Yes, yes, yes. So that is true. You scored 4. For what? Okay. So you scored 4 what, Aman? So are you telling me your advanced score? I don't know. Okay, so AP says M is 12, N is 12. So this would be again very very easy. Okay. So there are actually two ways of doing it. One would be the long method. Let's go by the long method first. So let's say that here is your cells. So all you need to remember is if there are let's say okay. No AP, that's not actually correct. Both are useful, trust me. Both are useful. Okay. So where did you score 4? I mean I don't understand what that is. So if you have identical cells like this, I hope you remember the formula for E equivalent. E equivalent over R equivalent is given by summation of EI over RI. And here because all the cells are identical, you realize R equivalent would be if there are m rows, right? Yeah, m rows and n series. So R equivalent would be n times R by m. Okay, so that should be easy to see. And similarly, here also for every cell, the E for every row, the E would be n times E. So what you will realize is that E equivalent would be R equivalent, which is n R over m into summation of. You realize this for every row the R would become nr and E would become ne. So it would be summation of E over R only. So that would be into m. So n times E. That is going to be your. I scored for a question in that quiz. That marks I thought gave me 4. Okay, okay. I don't remember exactly what you're talking about, but yes, I do remember telling this that yes, V is proportional to R T. Okay, okay. So now that you know this, now that you know the equivalent resistance and equivalent EMF, now you will know the value of current across this R. So let's try and see that. The value of current I across R would be again n times E over this entire unit, which is n R over M plus R. Okay. So now what will be the power across capital R? Power across capital R would be I square capital R. The power would be n square epsilon over n R over M plus R whole square into R. Again, for finding the maximum power, we are again going to do that only. We are going to find the dP over dr. So next we find dP over dr and put it to 0, and let's see what that gives me. dP over dr becoming 0 tells me n square E square over n r over m plus r square plus n square e r over. Okay, so in any case, I don't even need to do this, by the way. I don't even need to do this. I just realized that since I already know the equivalent EMF does not even matter. For any equivalent EMF, the power dissipated would be maximum as long as small r is equal to effective small r is equal to capital R. But still, let's just prove it. Let's just prove that. Okay, so into again minus 2 and over n over m r plus r to the power of 3 equals 0. You realize this is getting cancelled. This entire thing will get cancelled with this, and what you're getting is that n r over m plus capital R equals 2r. So again, you have the same result. You will realize that you have R equals NR over M, which is telling you that irrespective of what kind of circuit there is, the condition for maximum current and hence maximum power will always be that the internal resistance should be equal to the net external resistance. So which was the maximum power transfer theorem. So from that you will use this. So now you know. I just wanted to show you the proof that it will work even in such a situation. Now you can directly use this result that for any kind of configuration to deliver maximum power across capital R, what you need to do is make the internal resistance of the configuration of batteries to be equal to the external resistance of capital R. Now once you have done that, you know that this was, I think capital R was 5 and that was 0.5. So you know 5 equals n over m into 0.5, which tells me that n equals 10 m. And I also know n plus m should be equal to 24 if I think that has been told. Yes. So from here, so that should have been 22. Let's just make this 22 for the sake of simplicity. Otherwise, we are getting a fraction. So let's just make this 22 cells instead of 24. Now it will be easy. At least I'll get some nice even numbers. So if this was 22, then this is very easy now. That 11m equals 22, m equals 2 and n equals 20. So that will be the correct answer. Okay. So again, I hope everybody followed this. I hope everybody realized what we are doing. Again, I showed you the proof. Now you could have directly written also that with the help of maximum power transfer theorem, you know that the equivalent resistance of this, you would have had in every row, you would have had small r, n small r's, which would have given an equivalent of n times r, and you would have had m rows of this in parallel. So m rows of this in parallel would have made the equivalent internal resistance as nm over nr over capital M. And all you need to do was for maximum power to be dissipated against this should be equal to the net internal resistance of the battery. Use that fact, and then you would have straight away gotten this equation. You realize I spent all this time proving this. This was not required. This was already. That is why we have this theorem. Okay, so next time you see such a problem, you know what you have to do immediately. Okay, let's try one more. Now this one says that in the circuit shown below, find the value of R1 is 2 ohm and the load resistance is 12 ohm. you have to find the value of R2 for which maximum power dissipation across the load happens. So try this. So let's quickly try this. I still wanted to discuss a lot of things. So hurry up if you want everything to be discussed in time. Because there is a lot to discuss right now. So hurry up, let's solve this very quick. So again, I would encourage you to try. I mean, for the first time when you're trying, try solving everything by differentiation only. Do not use the power transference theorem, and then realize that it works in every situation. So here, how you will apply the maximum power transference theorem. By the way, think about it. Okay. So again, I don't want to wait for too long, and as I said, we are running out of time, and there is a lot that I want to discuss for today. So what we'll do is I just quickly solve this. So you realize that from maximum power transference theorem, you could know that the potential difference across this would be maximum if the equivalent resistance of this entire thing becomes equal to this. So we will use the fact, and you know that the power dissipated across this load would be maximum whenever the potential difference across this is maximum. So let's quickly try that. What will that tell me? That will tell me that this 2R should be equal to, so from maximum power transference theorem, now I will directly use this result. What I can say is that R1 should be equal to R2 times R load over R2 plus R load. Okay, why? This will be the equivalent resistance of R2 and R load. And if this becomes equal to R1, which essentially in this circuit is playing as the role of the internal resistance of the battery, then I should have maximum power transferred across the load. So let's solve this quickly. You know the value of R1 is given to you as 2. R2 is what you need to find, and load has been given to you as 12, if I remember that correctly. Yes. Okay, so let's just solve this very quick. So this is telling me that 12 plus R2 equals 6 R2, which is giving me the answer that R2 should be equal to 12 over 5, which is 2.4 ohm. So that is the answer that I have, 2.4 ohm. That if you keep that value of R2, then the power dissipated across the load resistance would be maximum. Okay. So now, if everybody is fine with this, let's move on to the next topic. Next topic, we will talk about appliances and rated powers. So you must have realized that whenever you look at any appliance, you would see that it always has a rated voltage. So you will realize every appliance comes with a rated voltage, and a rated power. So what are these things? What are these things? So for instance, what you can do is you can try this at your home. You can try this at your home. You can maybe take a look at the cardboard in which maybe your TV came, all right, or the packaging of your AC, the board cardboard that your AC came in. So you will realize when you are taking a look at all the specifications, it will say a rated voltage and a rated power. So what do these mean? See, the rated voltage is that this is the voltage at which you are meant to operate that device, and rated power means this is the power that it will consume when you run it at the rated voltage. Now, why do you have a rated voltage? Why can't you run it on any other voltage? Now, the reason for that is that every electronic device has some kind of circuit in which heat is getting generated, power is getting utilized. So every device is placed or given a resistance according to by imagining a certain power input. Okay, so imagine if I have a circuit which is intended to use a certain amount of power and run on a certain amount of current. So you realize if I want, see, I have already made the device, so its resistance is fixed. Now, if I made the resistance by assuming that if I current would be flowing across it, then this is the amount of heat it will generate, this is the amount of power it will derive, and this is how I want it to operate. So I have to assume a current I. Now for that I have to specify this, the battery of the power source as V would be equal to IR. So I already design every component by keeping in mind one I. Why do I do that? Again, because you realize this device is not a single resistor. This device may have a lot of things, a lot of components, maybe some resistances, there may be some capacitors, there may be some other circuit elements. So what happens is that this entire thing has been devised by assuming that it will have a certain potential difference across the ends. Okay, so that all the currents inside are distributing a certain way, and every part is getting an appropriate amount of current or energy to work. So you realize while designing the device, it was already assumed that I'm designing this considering that the potential difference across this would be 220, let's say, for example. So if that is 220, then I know this current would come into the device, this current would go into this branch, this current would go into this branch. So this part will get this much amount of power, this part will get this much amount of power. So that everything like that has to be considered when designing the device. So if you do not operate this on rated voltage, then what happens? Then of course the designer, whoever designed the circuit, had some ideas in his head. He had some intentions of certain currents flowing through the wires so that they are generating some amount of power. Now suppose if the I across any resistance is higher, then that may lead to damage of the device. Why? Because see, every circuit has wires, they are sensitive to heat. If the I is higher than the intended I, then it may create extra heat which maybe the circuit cannot withstand. So I don't want my current to be higher than the current for which it was designed initially. And if say it is lower, then it will not give you the desired output. So consider the example of a bulb. What happens in a bulb? So I hope you guys know that this is the circuit symbol of a bulb. Okay, this is what we use as a bulb. So every bulb, you will realize, has again a rated voltage and a rated power. Now rated power is usually defined by the supply power that you have. So for instance, in India, the supply voltage standard is 220 volt. In US, the supply voltage standard is 110 volt, by the way. So you realize that is why when you get devices from US and we try to use in India, you need a separate adapter to adjust the value of voltage. If you directly try and plug it in Indian circuits, it will blow. It will become damaged. So imagine this. Imagine this. When you go to the market, when you buy a bulb, see the bulb will say, let's say it says 60 watt and a 220 volt. So what that implies is that this bulb is meant to operate at 220 volts, and when you operate it at 220 volt, then it will consume 60 watt of power. Now you must have noticed that sometimes what happens is that the voltage is low in the supply. Then you will see that the bulb will be lighting very dim. So what is that causing is that if the current, as I said, every circuit was designed for a particular amount of current. If the current is lower because of lower potential difference, then I see it is not giving me the enough light that I wanted to get out of that bulb. I have that bulb switched on, but it's giving me hardly any light. I wanted more light. I got that 60 watt bulb because I needed more light. If I needed less light, I would have gotten a smaller bulb. So one problem would be if the current is lower, then first of all, the output will not be as desired. And suppose the voltage suddenly becomes very high, then you see the bulbs get fused. So that is the second problem. That if the current falls below, then the performance of the device is not at par at expectations or whatever you intended. If the current is much higher, then it may damage the device. So that is why you always want to run everything at the rated voltage. Okay. So rated voltage is the voltage at which the device should be run. So that is what the rated voltage is telling you. Okay, thank you, Adurity. Okay, that is what rated voltage is telling us, that you should run this device on this potential difference. And what does rated power tell us? Rated power tells us if you run the device at the rated voltage, then it will consume this amount of power. So please remember this. And then rated power is the amount of power that the device will consume when operated at the rated voltage. So please remember this. Okay, now I hope everybody should be clear about what rated power is, what rated voltage is. Now, in our home devices, you have fuses. So, what is the function of a fuse? So, fuse is a safety device essentially. So, I told you that if the current in any electrical device is higher than what it was designed for, then that may end up damaging the device. So, for that, to stop that from happening, what you have is that every electrical circuit has a fuse at the starting, and this fuse is connected in series with the device. So, for instance, your wire of your TV, say, will have a fuse at the end. Before the power is going into the TV, there would be a small fuse through which this power has to go. Same would be the case for most of your sensitive devices, and you will also have a primary fuse for the house also. In your household, first of all devices are connected in parallel. Why? Because every device was intended for a particular potential difference. So you realize the supply is given between two terminals which have a potential difference of, let's say, 220 volt. So how do you ensure that every device gets this? Very simple. You get every device in parallel. So that's the first thing that you would want to do. So in your home circuits, in your home circuits, all your devices, your fridge, your ACs, your TVs, everything is essentially connected in parallel, and everything is getting voltage, which is the supply voltage and also the rated voltage. Okay, so that's the first thing you need to remember. See, what that does is that also helps you in another thing. Okay, so in houses, all devices are connected in parallel. Now, that obviously has other benefits as well. For instance, suppose if I connected everything in series, now you realize now I have a problem. If I wanted to switch off TV, everything gets switched off. As long as they're in parallel, it doesn't matter. So let's say this was your AC, this was your TV. Okay, and this was your fridge, and so on, refrigerator. So you could switch individually devices on and off without affecting the others. Okay, because others are still having the same potential difference. If everything was in series, so first of all, you would have had this problem. The moment you would switch off your TV, the circuit would break and everything would get switched off. Right. So that is of course another reason why everything has to be kept in parallel. Now, as I said, what is a fuse? A fuse is a safety device which is connected in series with any of these devices. So you may have several fuses here. So you may have a fuse here, 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 or you may also have a fuse at the very entrance of the house. So your main MCBs, they also have fuses. Okay, so you must have experienced, okay, whenever electricity goes, sometimes the fuse box is checked and turns out the fuse wire got burned. So let's quickly just write about fuses. A fuse is a device connected in parallel, in series, in series with an electrical appliance or even a circuit, or a circuit to save it from getting damaged due to high currents. So how does it do that? So it's very simple. It's very simple. So every fuse wire, every device. So let's say whenever we are designing any device, let's say if the rated power was 220, and for the sake of simplicity, let's just assume that the rated voltage was 220 and rated power was also 220 only. Now I hope you will remember that power would be V into I, so which means that the current that the device is meant to operate on is, let's say, 1 ampere. So that does not really mean that the device will get damaged the moment the current reaches 1.1 ampere. So there is obviously some margin of error that is kept, and of course some extra heat anything would withstand. But there would be a limit beyond which you don't want to expose your device. So what happens is, let's say the maximum current that this device can, it is meant to operate at 1, and let's say the maximum it can go up to without affecting its performance too much is, let's say, 1.5 ampere. Now the fuse will have an element which is made up of something which will ensure if the current in this circuit becomes higher than 1.5, then the heat generated is so much that this guy will melt and end up breaking the circuit. Okay, so that is the kind of material that you will choose for fuse. So fuse ensures that only a certain maximum current can enter your circuit. If the value entering the circuit becomes higher than this, then the fuse wire melts because the heat produced is so much that it causes the melting of the fuse wire and it breaks the circuit and saves your devices from damage. Okay, so that's the idea of fuse. Now, also in your households, though you know the unit of energy is watt, but in your households you use another unit of energy, which is kilowatt hour. Kilowatt hour is the commercially used unit of energy, or electrical energy rather, energy consumed by electrical appliances. So yes, though you may have bulbs of 100 watt, 200 watt, 150 watt, maybe 50 watt, maybe 60 watt, but you realize you have another unit of measuring this, and when you get your bills, electricity bills, so there are something units. Okay, so your bill will say that your bill for this month is, let's say, 100 units. So what are those units? So one unit is 1 kilowatt hour. So you realize 1 kilowatt hour, what does that mean? You know that energy over time is power. So power or energy would be power into time. So that is what this unit is, kilowatt into hour. So if I convert everything into SI units, in SI, 1 kilowatt hour, let's see how much that becomes. 1 kilowatt becomes 1000 watts into 1 hour becomes 3600 seconds. So what you get is 3.6 million joules. So that is what 1 kilowatt hour is. 1 kilowatt hour is 3.6 million joules. Why do we use this? After NEET, one of my friends tested positive. Oh yes, I hope so too. Yeah. It is tough. It is tough that going out for this exam, taking that risk. So yes, but don't worry. I hope people will be better because the recovery rate is pretty good. So let's hope there is nothing much to worry. And especially for you young people, it should be fine. You guys are in your prime. You guys have great immunity. So I'm sure your friend will bounce back. She'll get back soon, better very very soon. Don't be sad. Yes, Papi. So one shot series waiting for what? Which one shot series? I already have that on the app. I told you. I already have that on the app. On the app, if you go, there are free special sessions that I have taken. Go to the free classes in the app. You will find my one shot sessions. Yes, for 11th. I have taken one shot for kinematics, one shot for Newton's laws, one shot for work power energy, one shot. Okay, so I will tell you, I have taken one shot for kinematics, Newton's laws, work power energy, momentum, rotation. Yes, I did a 3-part review. Okay, no, not only some chapters. I have done fluids, I have done gravitation, and I recently did thermodynamics. The only chapter, and I also did one for SHM. Only 2 chapters are missing. I have done one shots of around 7-8 chapters. Okay, only I think waves is missing right now, and maybe elasticity. Yes, you go through it. I have covered 80% of the syllabus in one shot lectures, or more than 80%. Don't worry, and rest will also be coming. Don't worry about it. Yes, you go to my profile and you check my lectures. You will find them. Okay, all right. So again, why do we use this unit, kilowatt hour? This is a practical unit. You realize if your house bills are coming as 100 units, 200 units, it is practically easier for us to deal with these numbers. Otherwise, imagine your bill to be 3.6 into 100. So imagine 100 units would have meant 3.6 into 10 to the power 9 joules. So it just doesn't feel very good. Seeing such big numbers. So just to keep these things practical, we use this unit. There is no other very great significance about having this system. It's just more convenient practically. All right, so why don't we start and practice some problems? So you've been told that an electric heater and electric bulb rated at 500 volts and 200 volts, 220 volt and 100 watt and again 220 volt respectively, both are connected in series with a 220 volt DC supply. Calculate the power consumed by both. Now, what will be the power consumed when both are connected in series? Now, in your households you would never do that, but suppose if you did, suppose if you connected two devices rated at 220 each in series, then what would have happened? What would be the power consumed by each? Let's try and solve this. This is one kind of question that is very frequently asked, not only in your mains but boards also. Maybe advanced wouldn't ask such questions, but this is important from your boards as well as mains point of view. So I would like you guys to give it a try, and let's give you 2 minutes to solve this. Okay, so we just have three more problems to discuss. That's about it. So yes, I'm glad I could discuss everything that I wanted to discuss today. Let's see you guys solve this quickly. I am giving you 1 more minute. Okay, so how do you solve this? Think about it. Just think about it. So whenever the question gives you all the rated power and the rated voltage, don't think about all that too much. Just think of it in terms of normal resistances, and you will be fine. Okay, that's my hint. Okay, so 2 minutes is over. Why don't I just solve it? So you've been told you have a heater and you have a bulb. So what we will do is that in our simplistic world, we will just represent them by two different races. Okay, let's call them R1 and R2. So R1 and R2. R1, let's say, is the heater and R2 represents the bulb. And you have connected both these to a supply of 220 volts. And of course, you have to consider that this this supply has no internal resistance, so that is what we are assuming, or it is the terminal voltage in any case that is always given to you as 220. So you have to calculate the power consumed by the heater and the bulb. So let's see what were the rated powers. The rated powers were 500 and 100. So this had rated power. The rated was 500. The rated dash was 100, and V rated of course for both was 220. So what I will do is that I will try and find the value of R1 and R2. See why? Because for finding the power that each of them are consuming, I need to know I across this circuit, and if I know I will know that the power across this would be I square R1 and power across this would be I square R2. Okay, so since I needed to calculate the power, I need the current, I need the resistances. So it is very simple. If I can find the value of R1 and R2, then everything is sorted, right? I can calculate I then using Ohm's law, and I square R1, I square R2 obviously would not be a problem. So how do I find R1 and R2? It is very simple. You have been told that at rated power, the rated power of heater is 500 watt at a rated voltage of 220. What does that mean? That tells me that the power it would have consumed when run at 220 volts would be 500, and you know that power was V into I You can also write this as I square I R, or you could have also written this as V square over R. So this is the formula that we always use for calculating the resistances with the help of rated powers. So you will use this relation, this and this being equal. You will realize that resistance of any device can be calculated as rated power, or sorry, V rated square over P rated. So that is what you are always going to do. Okay, so now let's just calculate these. So I have been told my heater has a rated power of 500 and a rated voltage of 220. So I can say R1 would be equal to 220 square over 500. Similarly, R2 would be 220 square over 100. Okay, now it's very simple. Now all I need to do is find the value of I. Okay, so R equivalent would be, so let's just add that. So let's just take 220 square over 500 common. What you have inside is into 6. So this is the R equivalent, making my current I equals, that would be 220 over this R equivalent. So 220 square, okay, why do I have 5? So over 220 squared into 6 into 500. So that is what I'm getting my current as. So current I'm getting as this over 220 into 6. Now it's very easy to calculate. The power across the heater would be I square R1. So now P heater equals I square R1. Let's see how much that is. So that would be 500 over 220 into 6 whole square into R1. R1 was 220 square over 500. So you will realize I am getting this and this completely cancelled. Okay, so this only one power is 1. So what I am getting is the answer as 500 over 36. That is the power that it ends up consuming, which would be less than 100 watt. Oh, less than, very less than 30 watt also, in fact. Okay, so this would be the answer. Similarly, how about the bulb? Let's see what the bulb is doing. Obviously, both of them will consume lesser power. Do not blindly make that power to be half. Do not blindly think that since they have been connected to 220, so half of it will get here, half of it will get here. No, that does not happen. The voltage will get divided according to the resistances. Okay, so do not think that the powers would be half and half. So a lot of students tend doing that. They tend to say immediately when they see this question, that's what it will be 250 and 50. No, that is not correct. You will have to calculate. It comes out to be some weird value. So again, when you calculate this for the second one, you have 500 over 220 into 6 whole square into R2. R2 was 220 whole square over 100. So this goes, and what you have is 5 into 500 over 36. So turns out this guy ends up consuming much more power than the other guy, at least. Okay, so this is 5 times more power than this. So bulb ends up consuming much higher power. Why? Because the bulb obviously had a greater resistance. Okay, so I hope this is clear to all. If you have any problem or any issue regarding this, how we solve this, then let me know. Otherwise, I will move forward. Okay, this is fairly easy. All you need to remember now is that for all such problems, you find the resistances of all your appliances by using this formula. So this is what is important. Pay attention to this. Once you know this, now convert any of the circuit into normal resistive circuits, and then you will not have a problem again. Okay, let's take a look at another problem quickly. So a heater coil is rated at 100 volt and 100 watt and 200 volt. Now it is cut into two identical parts. Both parts are connected together in parallel. The same source of 200. What will be the energy liberated per second in the new combination? So that should be very easy. What you will realize is that let's say the resistance of the device initially was R. So imagine if the device initially had a resistance of R, and let's say what you have been told that now it is cut into two identical parts and both the parts are connected in the parallel. So I will know that initially R would be equal to V rated, which is 200 square over 100, right? This we just saw in the last. Now all you need to do is that what they have told you that this is cut into two and those are connected in parallel. So you realize it will be like this, R by 2, R by 2, and these are connected in parallel with a battery of 220 volt. So you realize the R equivalent would be R by 4, and you realize if the power here is P dash, then you will realize P dash would be equal to V square over R equivalent, right? So what does that become? That becomes 2. Okay, so this is 200, right? Yes. So this becomes 200 square over R equivalent. R equivalent is this R over 4. Let's just write that down here. R equivalent would be capital R over 4. So capital R was 200 square into 100 and upon 4, so obviously you will have a 4 here. So now the new power would be 400 watt, and that is your correct answer. Okay. I hope everybody got that. Let me know if you have an issue regarding this. Otherwise, we will move on to the next and the last problem of the day, and then you can solve some problems on your own. Okay. Or maybe I can give you this as a homework problem only, because we have already crossed 5:30, and from 5:45, Abhinav sir starts his maths class, and I would like you guys to have a 10-minute break at least. So consider this to be your homework problem. We have discussed enough. You should be able to do that, and you should be solving other problems as well. So in this problem, you've been told three 60 watt 120 light bulbs are connected across a 120 power source. If the resistance of each bulb does not change with the current, then find out the total power delivered by the three bulbs. So you have three bulbs of 60 watt, rated power of 60 watt and rated voltage of 120 each. They have been connected as shown in the figure. Now why does it say that consider if the resistance of each bulb does not change with current? What does that mean? Why would it even change? Does the current change with does the resistance change with current? No, not really. It should have said with time. See, what will happen is that in electrical bulbs a lot of heat is generated, and when heat starts getting generated, then your resistivity increases and the resistance of these bulbs practically would actually go higher. Okay, so that you have to ignore, and this is the homework problem that you will try. Okay, and I will now see you on Saturday. Yes. So till then, you revise and you solve these problems. And before I leave you, let me remind you that this is how you should be getting your Plus subscriptions if you haven't gotten them already. So you go to the Plus in your Unacademy app, select your goal as IIT JEE, and you click on the Get Subscription. Now, when you come to the payment page, here you will be asked, do you have a code? Use this code ID Live and get a 10% off on all your subscription fees. Now, when you click on proceed to pay, you will be given a lot of payment options. You can break these payments into any number of comfortable, no cost EMIs, which do not make it a burden and do not pinch you guys. So Unacademy has taken care that nobody feels the burden of this fees. In any case, this fees is very competitive compared to what you guys pay in your offline setups. So trust me, anywhere in India, what you're paying here for 2 years, you pay double of this in 1 year, around double of this at least. That is for any of the standard coachings. Some coachings would even take more than that. So any normal coaching is charging at least 4 times this fees, and some top coachings also charge like 7 to 8 times this fees. So this fees is already very competitive. It also gives you a 10% off this if you use this code, and it also gives you a lot of payment options so that you can get quality education at without feeling the burden of money. Okay, so make sure you're getting these with this code. Next, if you're following us on the Unacademy JEE English channel, so that is, if you can't afford this, then you can always follow us here. The teachers are guiding you here and providing you all the quality content completely for free, courtesy Unacademy, of course. For that, you will need to connect with us on the Telegram app using the link shown above. Now, if you like today's video, then press the like button and share it with your friends. As I said, we want more and more students to benefit from this free quality content being given to you by Unacademy. So make sure it spreads, share it with all your friends and everybody who you think will benefit from this. And don't forget to press the bell icon. Now, the PDF of all the slides used in today's lecture would be available for download very soon. Next, before I take your leave, let me remind you that my code is RD Live. So remember to get your Unacademy subscriptions using this code and enjoy a 10% off on all your subscription fees. Now, I will see you next day after tomorrow, Saturday. Till then, you guys keep studying, keep practicing, and take care. Bye bye.